Today, we're building a cloud gaming service like NVIDIA GeForce Now, but without a user base and without access to sophisticated hardware. Our target locations are two: Middle East and Singapore. With all these requirements in hand, we want to maintain good unit economics. So how we build this? How we build a cloud gaming service? We select a cloud GPU and attach 1 TB storage volume. That storage volume contains the necessary games. We install Sunshine, Proton, Wine. We set up all these sophisticated technologies, and after that, we get ability to play Cyberpunk 2077 on Pentium 3. But the problem is that unit economics break this way. We have high data transfer for 1080p 60 FPS gaming. Now the problem here is not only the data egress, data problem is also with the data volume. Giving each user a node and a 1 TB storage volume, we are paying so much operational cost for one tenant. What can we do here? We can select Cloud GPU instance that is cost optimized. According to our research, Vast AI is the best platform. It is a P2P platform where we can find cost optimized GPUs. 0.058 per hour is the most cost optimized way we can leverage, but cannot play Cyberpunk 2077 on this GPU. We will need to pay at least 0.3 per hour, which is also cost optimized. But the problem here is not the cost, it is the geography. Most of the time, our target locations, which are Middle East and Singapore, they don't have the server in these locations. If we do leverage Vast AI, we will get to play 1 or 2 tenant, but after the third tenant kicks in, they will have to wait until the server is online. We have been discussing about the Linux Proton Wine approach, which is a shared resource approach. It is a translation layer that allows Linux to run Windows programs. Now, we also have another approach that we can run Windows programs on Linux operating system, and that is dedicated resource approach. In this approach, we essentially have Windows operating system that has direct access to the GPU, enabling us to have Windows operating system on top of Linux operating system with little to no overhead. But we went with the shared resource approach because we have much more exposure to the Linux ecosystem, and there are much more better sophisticated tools there that will enable us to leverage one node. Okay, now we can fix the unit economics in this architecture by leveraging spot compute, which gives a 35 to 45% discount on a node. We are playing a game on a dedicated storage volume. If a spot compute is taken away from us, all the game and start on all the progress, everything is taken away with it. Spot volume nature is like that. Despite we have the game in a new compute node, they can play the game there, but they don't have the same state. They will play from a new game and they will lose all the progress there. And it will be a very annoying experience. We must enable seamless experience so that the one user is leaving from one machine and migrating to the next machine, the state must be same. How can we do that? Introducing AWS infrastructure instant hot swap architecture. In essence, this architecture is operating with a network disk. They are fast network disks, not as fast as dedicated storage volume, but fast enough for a game. They are network disk. They have game and save game files and the state attached to the node. So when the death timer kicks in, we detach from that node and attach to the new spot compute node. The user will see a few seconds of migration and instantly play from where they left off. But how it works, how that enables a seamless experience. To eliminate this, we have hot swap architecture. We slam quick save. We upload the files to S3. We have files in S3, only the stateful files. We have tiny VM orchestrator that is looking and listening to this event of death timer. When it finds that a node is going to go down, it does all this process of saving the SIGBIM files, and it provisions a new node and detaches and attaches the EBS. We restore the state and execute automation script, and we continue play the game. Despite we achieved the best logic to handle this architecture, 9.6 per volume, 1.24 for data egress, and 0.4 for the per tenant, we are significantly increasing the cost to play the game in the cloud with this. Now, if we try to improve unit economics, we still fail. If we have 0 tenants at a time, we have these hovering network disks out there that we are paying for nothing. If we try to reduce that cost by making that network disk multi-attached to multiple nodes to reduce the EBS cost, we fail because when multiple games write to the same EBS disk, they will store stateful files, game files, which in turn corrupt the data and create a systemic failure. The first thing that we did was move away from AWS infrastructure to OCI infrastructure to resolve the data egress issue. OCI infrastructure gives us 10 terabyte for free per month, and the data egress cost after that, even if we burn 10 terabyte, it is also very cost optimized, making a SCI infrastructure a strategic choice, which is main driver in our previous architecture telemetry engine as well. And how we resolve the EBS issue that is hovering out there. What we do is when there are no tenants, we take data away from block volume and put it in LCI object storage. It is like S3 and it is very, very cost optimized. But when a new tenant comes back, a new network disk is provisioned at 120 VPU. We transfer the game from the backup. Now, the way backups work for the EBS is that when we execute the restore from the backup command, we don't actually transfer the files from backup to the network disk. What we actually get is permalinks, the symbolic links. These files are simply the reference to where they are in the OC object store. So when we try to read them, the system automatically directs us to the OC object storage and creating a massive latency. If we try to play a game like this, we will experience a massive stuttering and lagging. We execute this sequential read command that is going to read all the files from OC object storage and make them available in the disk. Now, only after we play the game, and by playing the game this way, we reduce and eliminate the stuttering. Now, this is the core of this architecture. We are going to operate with read-only and overlay FS architecture. The way it works is that we have one high-speed network disk. Each user needs to save 20 gigabytes of stateful files and game files. We give each tenant 20 gigabytes separately. What we get with this architecture is that when we are playing a game, we are reading the assets, the necessary stats, the character, the buildings, everything is read from this high speed read-only drive. And when the system wants to write anything, the stateful files and anything, using overlay FS controller, they are saved in a different block volume. So what this architecture gives us is that the read-only drive can give access up to 8 nodes. Now, if each node can handle 100 tenants, we can leverage one network disk for over 800 tenants, which are all contributing to pay for one network disk. We give separate 20 gigabytes to each tenant. So if we take reference from this architecture, if one node can handle 56 tenants, we are giving 1.1 terabyte of block storage for stateful file storing. That 1.1 terabyte is responsible for storing all the 56 tenants stateful files in one place. We selected BM GPU RTX Pro 8. which gives 8 GPUs, and each GPU has 96 GB video RAM. Squeeze 56 tenants in there. Each tenant will be paying 0.6 for this compute node. We have one read-only master volume that costs $350 per month. It is a shared read-only network disk, local block volume that is used for storing the stateful files. If we get more tenants, we will be leveraging much more powerful machines, and there, consequently, we will be increasing the 448 tenants limit to well over 600, 800 tenants, which will decrease the master storage unit cost significantly. In the end, if we strategically select the hardware from the OCI infrastructure, they have sophisticated machines with modern architecture. They can enable us to have ray tracing DLSS at high settings to play games at 1080p with 60 FPS. The gaming experience will be phenomenal. One important thing to note is that after we transitioned from AWS infrastructure to OCI infrastructure, we selected this node, and this node did not have a spot compute option because this is highly leveraged, high demand node. If we are leveraging this on-demand compute, we will have uninterruptible gaming experience. No need to migrate. But our in-hot swap architecture still remains. The problem here for us specifically is that we don't have user base at the start. Unlike the NVIDIA GeForce, and they never have the idle hardware. They constantly have users utilizing the hardware. Now, in our case, for example, if we only have 5 tenants, using a machine that can handle 56 tenants, we are overpaying for the machine, and the unit economics will break this way. To resolve the issue, we have A10 nodes. These are cost-optimized nodes that can handle less number of tenants. We can leverage them when we have less number of tenants online. But when the number of tenants increase, we migrate those tenants from the A10 node to the RTX Pro node. This way, if we leave them running on the A10 node, we will be using the limit we have with the network disk. Now, this is how we determine how many tenants can fit in a node. We don't run a game on a node and see how much percentage it is using. So, for example, if we play Cyberpunk 2077 on the RTX Pro 8, we will be using 50% or 60% of GPU, which in essence, by math, we will consider that that node can only handle 2 to 3 tenants. That is not true. The machine is much more powerful. We leverage Linux isolation system at the kernel level. We take a slice of the hardware and give it to the game, and we see how much it is using it, how well it is performing it. When we create and test it in the isolation system, the game engine does not become greedy, read cache files and increase the usage percentage. This way, we find the true limit of how many tenants can fit in there. The common misconception: if there are 448 concurrent tenants and they're all using the same read-only drive, will that drive not become a bottleneck? So if we consider the previous scenario where we were handling 448 tenants through one read-only system, we are getting on the 5.98 megabytes per tenant. That is very, very slow. We cannot play the game with this speed because it doesn't work this way. Because of the NVMe off backend technology, we are only reading the files only once, and these 8 nodes, despite one node can handle 56 tenants, one node only has to read only once, and 56 tenants read directly from the RAM. 56 tenants don't constantly ask for the files from the network disk. Now, there is a problem that we identified. If all 56 tenants play different game, each and every single tenant, we will be reading different files. One node will saturate the network disk. So at the application logic layer, it will be better if we limit number of games a node can handle. Just like that, we build cloud gaming business service. Thank you so much for watching. Abdullah Memon, Principal Architect, Memon Systems.